Hello, everybody. I'm very glad to give this talk to the bright students of the Nuclear Engineering Master Program at Pisa University. My talk is about the virtual reactor, which is a computerized simulator of a nuclear reactor. In the past, a reactor simulator had to be made with a lot of approximations and simplifications because of the insufficient computing power. Therefore, the solution fidelity was not enough to replace verification experiment. Rather, some empirical formulas obtained from the experiment had to be provided to the simulation codes. But now with the enormous increase in the computing power, particularly with the GPUs, and also with the continued development of the modeling method, it would be possible to make high-fidelity simulators which can faithfully represent the reality. Then these high-fidelity simulators, or virtual reactors, can be used to accelerate the development of advanced reactors by reducing the required experiments and by raising the confidence on the predicted reactor power behavior. I'm going to talk about this possibility in this talk. First, I will start with the difficulty of high-fidelity reactor simulation and talk about conventional reactor simulation, which had to involve approximations and simplifications. I will then present the elements of the virtual reactors for advanced reactor development after showing various advanced reactors under development, which are much more complicated than the conventional ones, so that more sophisticated modeling is necessary. Then I will introduce the GPU-based high-performance simulation involving Monte Carlo and CFD calculations. Finally, I will touch the potential of machine learning and digital twins to be used in virtual reactors. This is a nuclear reactor which consists of fuel assemblies and coolant. Each of these tiny regions in the fuel and coolant has different power and temperature. The total number of regions to be traced is more than 760 million, which is a very large number. The power and temperature distributions are determined as the result of the interaction between several physics phenomena occurring in a reactor. Nuclear reactions including fission, scattering, heat transfer in the fuel and coolant, thermal expansion of structural materials, and material degradation involving corrosion occurs mutually affecting each other. In order to determine the power and temperature in each tiny region, these governing equations for neutron and temperature fields need to be solved. The temperature field is governed by the Boltzmann transport equation. The fuel temperature is determined by solving the heat conduction equation. And the coolant temperature field is governed by the mass, momentum, and energy conservation equations. The momentum conservation equation is the Navier-Stokes equation. All these equations are first principle equations. The first principle-based core calculation is, however, very difficult because of several reasons. The most important reason is the complicated dependence of cross-sections on energy as demonstrated by this resonance behavior. The macroscopic cross-section is affected by temperature through the strong temperature dependence of microscopic cross-sections and material density. In coolant, flow turbulence and boiling heat transfer makes it difficult to solve the Navier-Stokes equation as is. Therefore, several approximations and simplifications were introduced in the conventional reactor calculation. Multi-group approximation of the cross-sections, homogenization of materials in the unit of assembly, and diffusion approximation are those introduced to the neutronics side. In the thermohydraulics side, various empirical correlations such as Dieter's-Bolte equation for heat transfer coefficient, drag coefficient, turbulence mixing coefficient were introduced. Therefore, prior experiments were essential to generate these correlations. In addition, simplification of the flow as 1D flow is introduced not only in the coolant pipes but also in the core as parallel 1D flow channels. The Parks code, which I wrote when I was a graduate student at Purdue University back in 1995, was a typical conventional reactor simulation code based on these approximations and simplifications. Even though the code was based on the two-group neutron diffusion equation, the solver must be good for accurate solution and for fast execution. This is the result of the Parks calculation for a control rod ejection benchmark problem. It shows that the reactor power approaches to the asymptotic level after the power pulse due to the strong Doppler feedback associated with the rapid fuel temperature rise. This is the core power distribution, which shows a very high peak at the ejected rod position. It is noted that the power distribution is shown in the unit of core assembly, not pinwise. It is because each assembly is represented by homogenized cross-sections. In 2002, it was possible to obtain detailed sub-pin level power distribution through direct whole core calculation, which does not involve any homogenization. At the time, I led the numerical nuclear reactor project as the Korean side PI of an INERI program. This project was to challenge the first principle-based core calculation by solving the Boltzmann transport equation directly for the whole core, exploiting the parallel computing power of Linux clusters. The product was the Descartes direct whole core calculation code. Although direct whole core calculation was intended, the solution of the Boltzmann transport equation for the entire 3D domain was not possible because the computational burden is too high. Therefore, I introduced a novel idea of performing the transport calculation for each plane by using two-dimensional MOC, namely method of characteristics transport solver. Each 2D transport solution, which is obtained with explicit sub-pin level geometry, is then used to generate pin homogenized cross-sections for each plane. Then the 3D problem is solved with the pin homogenized cross-sections in the coarse mesh finite difference framework, namely CMFD framework. This method was named as planar MOC-based 3D CMFD calculation scheme. This was a breakthrough method that enabled direct whole core calculation on the Linux cluster at the time. Later, this method was adopted in the MPACT code, which was the direct whole core solver of the Vera, which was developed by the Castle project. Castle project was a U.S. government-funded big project for high-fidelity multi-physics reactor simulation. The term virtual reactor instead of a numerical reactor was first used when they constituted Vera by combining the impact neutronics code, the CTF thermohydraulics code, and the Mamba water chemistry code. Vera demonstrated impressive performance in the simulation of so-called crud-induced power shift, or CIPS, of the Watts-Bar Unit 1 nuclear power plant. In cycle 7 of Watts-Bar Unit 1, it was observed that axial power distribution is bottom skewed. Namely, the power is more shifted to the bottom than predicted in the cycle design calculation. Later, it turned out that it is because of the crud formation at the top of the core, which is hotter than bottom. The crud absorbs boron in the coolant, so that the boron is deposited at the top, causing the power shift to the bottom. Vera simulation result clearly showed this multi-physics phenomena as shown here. Without the modeling of crud by Mamba, the axial offset behavior shown here as this purple line is quite away from the measured values shown here with blue squares. With Mamba, the axial power shape shown here with the green lines matches well with the measurement, which is shown with the red circle. This spike here in the axial offset was due to the cleaning of the crud, which resulted in the removal of power shift. Vera predicted this spike very well, as shown with this green triangles. This Vera demonstration of the CIPS clearly shows the value of the virtual reactor for conventional reactors. Now let me move to the topic of virtual reactor for advanced reactors. These 7 SMRs are the typical water-cooled advanced reactors under development in various countries. These 4 are integral reactors in which all the major components are placed in a reactor vessel. This integration makes the flow path complicated so that 1D flow simplification cannot be used. Some of them do not use soluble boron, so that control rods and burnable poisons are extensively used to make the core very heterogeneous. In terms of both neutronics and thermohydraulics, these water-cooled SMRs pose challenges in the core calculation. The core calculation challenge is even bigger for the non-water-cooled reactors. These are sodium-cooled and lead-cooled fast reactors under development, and these are pebble-type and block-type gas-cooled reactors, and these are molten salt reactors with the molten fuel or solid fuel. The advanced reactors in general have complicated geometry with severe heterogeneity. In gas-cooled reactors, which uses tiny trees of fuel elements, the heterogeneity is even severe, so that so-called double heterogeneity is present. The cores are small, resulting in high leakage. In the core with the severe heterogeneity and high leakage, the diffusion theory is not valid, so that transport solution need to be obtained for the entire core. Slow flow speed associated with passive cooling would require delicate fluid modeling. The corrosion issue in the molten salt environment must be properly mitigated. In this regard, sophisticated multiphysics modeling involving neutronics with continuous energy Monte Carlo, thermal hydraulics with the CFD, and material degradation analysis with the atomistic scale material simulations are required to obtain sufficient solution fidelity. All these calculation models require enormous computing power. Fortunately, the GPUs, which outperform CPUs, can be effectively used to mitigate the enormous computing power requirement for high-fidelity analysis of advanced reactors. GPUs can yield high computing throughput by massively parallel SIMD and vector processing. Let me show you the power of GPU in SIMD, namely single instruction multiple data mode.
Let me speed it up.
This is for comparison, and this is a serial mode. Now this is SIMD mode, parallel.
Ladies and gentlemen, science class is now over.
The instruction to mix three basic RGB colors to produce a specific color in each cell is the same. Only the mixing ratios are given differently with different data set for each pixel. In order to fully utilize the superior parallel computing power of GPUs, the computer code should be carefully written to fully exploit the SIMD operation. This is a new challenge in GPU programming. Another challenge is related with the small onboard memory of a GPU. Special care must be taken for efficient memory management. At Korea Atomic Energy Research Institute, we identified the elements of the virtual reactors for advanced reactor development as this. The first is neutronics with the GPU-based Monte Carlo code. The second is higher order DNS, namely direct numerical simulation, for the solution of the Navier-Stokes equation. The third is CFD with the physics-informed AI. The fourth is atomistic material simulation using machine learning-based interatomic potential. Most of them involve extensive use of GPUs. Now let me talk about each subject one by one. At my Reactor Physics Research Group at Seoul National University, we have been developing a GPU-based Monte Carlo code with thermal feedback for superior computing performance in power reactor calculations. It has a specialized geometry module for fast execution in regularly structured cores. For general geometry application, it uses the finite elements and the optics ray tracing engine of NVIDIA. In order to maximize SIMD programming, many innovative methods, including event-based tracking, were developed. And also, efficient memory management was achieved by automatic domain decomposition. In most Monte Carlo codes, the history-based tracking scheme is used. This is to let each calculation thread track a neutron, which would yield its own collision history that will be different from others. Then each thread should execute different instructions because the collision of each neutron is random. This is not SIMD operation. On the contrary, in the event-based tracking, neutrons undergoing the same event, such as capture, scattering or fission, are processed together by the same instruction. By a sorting algorithm, it is possible to collect neutrons undergoing the same event. This is to fully utilize the SIMD operation. In the event-based scheme, one computing thread will track different neutrons at different times. The automatic domain decomposition scheme, as shown here, is also essential in GPU computing because the memory on a GPU card is not enough to contain the whole geometry information of the whole core. These two examples show that elaborate programming is essential in GPU computing. Pragma's superior computing performance was verified through the Weaver's real core benchmark problem. By using 24 commodity GPUs, the two-cycle depletion calculations with full thermal feedback could be completed within a day. Of course, the results are very accurate and detailed. No Monte Carlo code can perform this fast calculation at this low cost. In general geometry representation in Pragma, all the objects are represented by finite elements of these four types. The optics ray tracing module in CUDA is used to trace neutrons instead of light. Optics provide very efficient searching tool for finding the next intersection of a neutron track with an element by so-called bounding volume hierarchy algorithm. This is the result of the Pragma calculation performed with the optics ray tracing for the megapower heat pipe reactor, in which fuel rods and heat pipes are placed in a monolith structure. 31 minutes with the 24 GPs was enough to obtain this power and temperature distributions. In order to handle the special structures of the pebble type and block type gas-cooled reactors, sphere and cylinder objects was especially added as TRISO container. The core geometry is then described by an overlay of a finite element mesh structure and the two TRISO containers. The location of each tiny TRISO is explicitly determined by a rejection algorithm. The three-layer material within each TRISO are explicitly represented as well. The delta tracking scheme is used to avoid overly frequent TRISO region search. This is the Pragma result for a block type gas-cooled reactor. The calculation time is only 2 hours with the 24 GPUs. This one is the Pragma result for a pebble bed type reactor. The location of each pebble was determined by the SOFIA smoothed particle hydrodynamics code, which can simulate the pebble packing like this. This is the resulting pebble distribution, and this is the power and flux distribution. In the graphite reflector represented by finite elements, only flux distribution is shown. Now let me move to the topic of direct numerical simulation for the solution of Navier-Stokes equation on GPUs. In most CFD codes, the length, namely Reynolds averaged Navier-Stokes model is used. Length involves averaging of the Reynolds stress terms, and empirical models are employed to properly represent the stress term in various conditions. DNS is required to avoid using the empirical term, but DNS requires extremely small finite elements in general so that it takes a huge computing time. If a higher order method is used to represent the internal variation within an element, larger elements can be used for the same extent of accuracy. However, the higher order approach, with the higher order approach, the solution for each element would cause an increase in computing operation. This increase in element-wise computing operation is well suited to GPUs. At Argonne National Lab, they ported the NEC 5000 CFD code onto GPUs by employing a higher order scheme called spectral element method. And it was applied to a molten salt reactor analysis. At Cary, we are investigating hybridized discontinuous Galerkin method for more efficient GPU parallelization of DNS. It is named DYNA, which stands for Direct Numerical Simulation for Advanced Reactors using hybridized discontinuous Galerkin method. This shows the effectiveness of DYNA in a driven cavity problem. With the 6th order, only 18 meshes, 18 coarse meshes were enough to reproduce the fine mesh solution as shown here. Now let me move to the next subject involving machine learning. GPUs are known to be adequate for neural networks. For training a neural network, either model parallelism or data parallelism can be applied. The model parallelism is to use a GPU in a different layer of a neural network. This is needed to construct a big neural network for deep learning. The data parallelism is to use the same neural network in different GPUs. It is to use each GPU to train with different input sets. This is for big data applications. When solving a physical problem in which a particular physical governing equation can apply, it would be better to train a neural network with the physics constraint. It is called physics-informed machine learning. Once a neural network gives a trial output set consisting of spatial distributions of physical quantities, the output set is given to a residual evaluator network which can evaluate derivatives from the distribution and calculate the residual, which is the difference between the left and the right hand side of the governing equation at each spatial point. The residual information is fed back to the neural network so that the neural network parameters are adjusted to minimize the residue. This is one way of physics-informed machine learning. The basic training data are generated from high-fidelity computed solutions at limited conditions. CFD is a good area of physics-informed machine learning. This is an example which involves 10 CFD solutions for a 2D flow around a cylinder. 4 CFD solutions were generated with different aspect ratios of the cylinder, 3 with different angle of attack, 3 with different viscosities. These are the 2 governing equations of the flow which will be used for the residual evaluation through differentiation. These videos compare the goodness of the physics-informed machine learning for continuously varying angle of attack, aspect ratio, and viscosity. The result shown above was obtained by training with the 10 sets of data only. The bottom ones were trained with the data and physics as well. Obviously, the bottom ones are much closer to the reality. Atomistic material simulation, represented typically by molecular dynamics, are used to predict material characteristics such as impurity behavior or solubility. For molecular dynamics calculations, interatomic potential, shown as this, is used in the solution of the Newton equation of motion for a group of atoms given in a lattice structure like this. The interatomic potential can be obtained by quantum mechanics calculation, which takes a lot of computing time. Machine learning can be used to generate interatomic potential generated from some selected structures as illustrated with big circles and these selected structures. The red lines are those generated after machine learning on a neural network. This entire loop shown here is an active learning process in which the new structures beyond the prior range are suggested by the transient molecular dynamics calculation. For the new structures, the quantum mechanics calculations are additionally performed. This active learning process makes the machine learning more accurate and powerful. This movie demonstrates the molecular dynamics simulation of liquid sodium with the gas oxygen. The interatomic potential for this calculation was obtained by active machine learning. Once this kind of molecular dynamics calculation can be readily performed, a large number of combinations of the liquid metal elements can be examined to find an alloy that has benign characteristics, so it can be used in new material development. Finally, let me show you a digital twin of the Korean APR 1400 power plant. It is a replica of a real plant and was generated from the CAD drawings. By integrating monitoring data and simulation engines, the local states of the plant can be realistically followed. Now let's go into the turbine building, and we'll see soon the pressure and temperature at the inlet of the turbine and also at the outlet of the turbine. The maintenance record can also be accumulated for each part. This kind of digital twin will help the safe and high performance operation of the plant. This is a water drone which is used for the inspection of the filters in the internal refueling water storage tank. Now let me conclude. By exploiting the increased computing power, it is now possible to build a virtual reactor with the first principle-based modeling and simulation of each physical phenomena. Examples are Monte Carlo neutronics, DNS of Navier-Stokes, and atomistic material simulation. The virtual reactors will be useful for accelerating advanced reactor development by saving time and resources needed for experiment. The enormous computing power requirement can be resolved by using GPUs and elaborated programming. Proper SIMD-based parallelization and efficient memory management are necessary to fully utilize the capability of GPUs. Machine learning can also be a promising way. Yet, a lot of further development ought to be done to realize virtual reactors, and it is up to you, young folks. Thank you for attention. While you are thinking of the questions, let me show additional digital twin of APR 1400. Now we are going into the containment building to see the reactors and other entry press system. So this is the reactor, steam generator, two big steam generators. And so I think this is a pressurizer. So now we'll go to the bottom of the reactor. If you go down further, we'll see the internal refueling water storage tank inside. Now we are going up. Again, reactor vessel, waste pump. Anyway, I think this is fascinating. The digital twins can be made as accurate as this. Okay, now we are done.